You probably know the first expression, which is basically just the definition of the Euler-Mascheroni constant. Yeah, Euler-Mascheroni constant. Basically, they found out that the difference of the gth harmonic number and the logarithm of g, yeah, where while g goes to infinity, this difference like converges to a certain constant, which is known as Euler-Mascheroni constant. Yeah. I guess you know about the jth harmonic number as well. Jth harmonic number is just a discrete form of the sum. Yeah, basically 1 plus 1 by 2 plus 1 by 3 up to g. Yeah. But whereas ln of g is actually the integral form, basically from 1 to g of 1 by g dg. Yeah. These two are this is a discrete form, this is continuous form, and their difference like converges to a constant which is known as Euler-Mascheroni constant. You probably knew this earlier, yeah. But in this video, there is something different. It's about difference with basically these are same thing, log and ln. Difference with the ln, but here we have an modified cosine integral function. So basically, this sin cosine integral function is defined as integral from 0 to g of 1 minus cos t by t dt. And let's try to define log in a similar manner. Yeah. Okay, so if we had to take it from 0 to g, for this one as well, if we take it from 0 to g, since we cannot really evaluate log of 0, so we have to write it down t plus 1 dt. Yeah. But then again, there's another problem, because if we now evaluate this, we get ln of g plus 1 minus ln of 1, we get this. But we actually wanted log of g. Yeah. But the fact is, at infinity, at g goes to infinity, log of g and log of g plus 1 are actually equal. So that's why this will not really be a problem. Let me prove like why they will be equal. Let's say we have g going to infinity. We have find the difference of log of g plus 1 and log of g. Yeah, we will see that this difference will actually goes to 0. That's why both of them will be equal. 1 plus 1 by z. Now since g goes to infinity, we have 1 plus 0 and log of 1 is just 0. So that's why we can see that this is 0. That's why both of them are equal at g goes to infinity. Yeah. So now we have the integral expression for both the terms. Limit g goes to infinity, cosine integral function of g is basically integral from 0 to g of 1 minus cos t by t dt minus this one is integral from 0 to g 1 by t plus 1 dt. Yes. Now since both of them are like defined convergent integrals, we can group them. Limit g goes to 0, integral from 0 to g 1 minus cos t, and then again 1 by t, let's say, minus cos t by t, and then minus 1 by t plus 1, yeah, dt. Now let's group these rational functions. Limit g goes to 0, if we group them, we get integral from 0 to g of 1 by t plus 1 minus t is basically 1, so 1 by t times t plus 1 minus cos of t by t dt. Now at this point a slight observation is needed, yeah, to make things go forward. And the observation is now t is not going to 0, basically t is going to infinity. Sorry, g is going to infinity. I'm sorry for this. I'm sorry for all of this. Infinity. This is basically infinity. Limit goes to infinity. Yeah. Now you can write this as t to the power minus 1 by t plus 1 minus, this can also be written as t to the power minus 1 cos of t dt. Yeah. Now if we look at -1 as s minus 1, yeah, basically what we can do is, let us say a new variable s which is going to 0, yeah, and then let us say now let's write 0 to infinity itself. We can now say that this is just e to the power s minus 1 by 1 plus t dt. Similarly, minus integral from 0 to infinity t to the power s minus 1 cos of t dt. Yeah, this is because now we can use the beta gamma function, and over here the Mellin transform. Yeah, limit s goes to 0. Over here that will be gamma of s, gamma of 1 minus s, and the problem is cannot really find gamma of 0, but we will deal with limits where we will be able to find minus. And now the Mellin transform of cos of t is basically gamma of s and then cos of pi s by 2. Yeah. Now to evaluate this, we should basically have gamma of s plus 1. Yeah, that's why what we will do is this gamma of s plus 1 and gamma of 1 minus 1, again gamma of s plus 1 and then cos of pi s by 2. Yeah, but since we need just the gamma of s, let's divide this by s, so that gamma of s plus 1 by s is gamma of s, gamma of s plus 1 by s is gamma of s. Yeah. Now to evaluate this is basically in the L'Hopital's rule form. Yeah, this is 0 by, okay, so this is basically 1 minus 1. Yeah, so 0 by 0 form. So let's use L'Hopital's rule and differentiate both the sides. Before we use L'Hopital's rule, let us also take the common. Let us take gamma s plus 1 common, and then we will use L'Hopital's rule. Gamma of 1 minus s minus cos of pi s by 2 by s. Okay, so now let's use L'Hopital's rule and differentiate numerator and denominator. Limit s goes to 0, gamma times s plus 1, yeah, and gamma of 1 minus s minus cos pi s by 2, yeah, and then now gamma of s plus 1 as it is, derivative further is, other expression is gamma times of 1 minus s times minus 1 minus, and minus is now plus, sine pi s by 2 times pi by 2. Yeah, and the derivative of s is just 1. Now let's substitute s as 0. We have gamma times of 1, gamma of 1 minus cos of 0, yeah, and then plus gamma of 1. Over here we have minus gamma times of 1, and then this is just plus 0. Yes, so now we finally have over here we have gamma times of 1, and then this is just 1 minus 1, so it's 0, and over here it's minus of gamma times of 1. We know that gamma times of 1 is negative Euler-Mascheroni constant, so this will just be Euler-Mascheroni constant, and that is the answer. Yeah. Whew. So we finally found that this limit is Euler-Mascheroni constant. Talk about the flow. Use the integral representation and just subtraction, and an observation that we can basically let s go to 0, and then use the s minus 1 notation, yeah, and so that we can use the gamma function, we can use the Mellin transform, yeah, and after that we did see that it's not evaluatable, but using taking it to a fraction form and then using L'Hopital's rule, we could evaluate it in the limit, yeah, and then we got the answer that it's actually Euler-Mascheroni constant. Yeah. So that was it. Hope you enjoyed the video. Hope you got some new insight. Hope you got some new formula to like brag with your friends. Yeah, I hope that helps you. Thanks for watching, and look forward to seeing the upcoming videos too.